Welcome back to JVM Internals Crashcasts. I'm your host Sheila, and today we're wrapping up our chapter on Introduction to the JVM with a deep dive into the basic architecture overview of the Java virtual machine. Joining me as always is our JVM expert, Victor. Hey Victor, ready to unravel the JVM's architecture for our listeners?
Absolutely, Sheila. I'm excited to break down the JVM's architecture and help our listeners understand how this powerful virtual machine operates under the hood.
Great. Before we dive in, let's remind our listeners that we've already covered what the JVM is and how it differs from the JRE and JDK. Today, we'll be building on that foundation to understand the core components that make up the JVM's architecture. But first, let's start with a fun quiz question for our listeners. Victor, would you like to do the honors?
Certainly. Here's a question to get our listeners thinking. Which component of the JVM is responsible for converting Java bytecode into machine code? Is it A, the class loader, B, the execution engine, C, the runtime data areas, or D, the native method interface? Think about it, and we'll reveal the answer at the end of the episode.
Ooh, that's a tricky one. I'm sure our listeners will be pondering that as we go through the episode. Now let's start with the basics. Victor, can you give us a high-level overview of the JVM's architecture?
Of course, Sheila. At its core, the JVM architecture consists of four main components: the class loader, runtime data areas, execution engine, and native method interface. Think of the JVM as a well-oiled machine, where each of these components plays a crucial role in running Java applications efficiently.
That's a great starting point, Victor. To help our listeners visualize this, could we compare the JVM to something more familiar, like a factory perhaps?
Excellent idea, Sheila. Let's imagine the JVM as a high-tech factory. The class loader is like the receiving department, bringing in raw materials, Java bytecode, and preparing them for processing. The runtime data areas are like various storage facilities and workbenches where materials and partially finished products are kept. The execution engine is the main production line, transforming the prepared materials into finished products, executed code. Finally, the native method interface is like a specialized workshop that can handle custom orders, native code, that our main production line can't process directly.
That's a fantastic analogy, Victor. It really helps to visualize how these components work together. Let's dive a bit deeper into each component. Could you start by explaining the class loader in more detail?
Certainly. The class loader is responsible for loading, linking, and initializing Java classes and interfaces. It reads the .class files, checks their correctness, and places the binary data of the class in the method area. It's a crucial part of the JVM's security model, as it ensures that only valid bytecode is executed.
Interesting. So, the class loader is like a gatekeeper for our Java code. Now, let's move on to the next component. What about the runtime data areas? I've heard terms like heap and stack before. Are these related?
You're absolutely right, Sheila. The runtime data areas include several key memory areas. 1. The heap. This is where all objects are allocated. 2. The stack. Each thread has its own stack, storing local variables and partial results. 3. The method area. It stores class structures, methods, and constant runtime pool. 4. The program counter, PC. Register. It contains the address of the JVM instruction currently being executed. 5. Native method stacks, used for executing native methods.
Wow, that's quite a bit to take in. It sounds like the runtime data areas are the JVM's memory management system. Now, let's move on to the execution engine. I'm guessing this is where the actual code execution happens.
Exactly, Sheila. The execution engine is the heart of the JVM. It reads the bytecode stored in the runtime data areas and executes it piece by piece. It includes three key parts. 1. The interpreter executes bytecode instructions directly. 2. The just-in-time (GT) compiler compiles frequently executed bytecode to native machine code for improved performance. 3. The garbage collector automatically frees up memory by removing unreferenced objects.
That's fascinating, Victor. The JIT compiler sounds particularly interesting. It's like the JVM is constantly optimizing itself. Lastly, could you explain the native method interface?
Of course, the native method interface, often referred to as Java Native Interface, or JNI, is a framework that enables Java code to call and be called by native applications and libraries written in other languages like C, C++, or assembly. It's crucial for operations that require direct interaction with the underlying hardware or operating system.
Thank you, Victor. That gives us a comprehensive overview of the JVM's architecture. Now let's address some common misconceptions. One I've heard is that the JVM is slow because it interprets code. Can you clarify this?
Absolutely, Sheila. While it's true that interpreted code can be slower than native code, modern JVMs use sophisticated GT compilation techniques to optimize frequently executed code paths. This means that Java applications can often perform as well as, or sometimes even better than, natively compiled languages.
That's really interesting, Victor. It seems like the JVM's architecture is designed for both flexibility and performance. Before we wrap up, do you have any tips for our listeners who might be developing or optimizing Java applications?
Great question, Sheila. One key tip is to be mindful of object creation and memory usage, as this can greatly affect the garbage collector's performance. Also, understanding how the JIT compiler works can help you write code that's more likely to be optimized. Lastly, for performance-critical sections, consider using JMH, or Java Micro Benchmark Harness, to measure and optimize your code.
Those are excellent tips, Victor. Now, let's reveal the answer to our quiz question. Which component of the JVM is responsible for converting Java bytecode into machine code?
The correct answer is B, the execution engine. Specifically, it's the JIT compiler within the execution engine that performs this conversion. Great question to test our listeners' understanding.
Indeed. To summarize today's episode, we've explored the four main components of the JVM's architecture: the class loader, runtime data areas, execution engine, and native method interface. We've seen how these components work together like a well-organized factory to execute Java code efficiently and securely. In our next episode, we'll be starting a new chapter on core concepts, beginning with class loading and linking. We'll dive deeper into how the JVM prepares classes for execution. If you've enjoyed this episode, please don't forget to subscribe to JVM Internals Crashcasts and leave us a rating. Your support helps us continue creating in-depth content about the Java virtual machine. Until next time, happy coding!